Hello, and welcome to part 3 of chapter 22. In this short part, we are going to look at the Hoffmann elimination. Now, this name should sound very familiar to you. We in Organic 1 learned about eliminations. We started with alkyl halides. We know that if we use a smaller base, like a sodium hydroxide, we will wind up with the more substituted Zaitsev product. But if we use a bulky base, that we will wind up with the less substituted Hoffmann product. That relies on the base being bulky. When we look at hydroxys and amines, you can eliminate a hydroxyl group using concentrated H2SO4, but that would give a Zaitsev product. Or you could use something like tosyl chloride or PBr3, make the OH a better leaving group, and then use your bulky base and get the Hoffmann product. Now, amines are also not good leaving groups, much like the hydroxy group. And so in this reaction, we have to make it a better leaving group. Now, instead of using acid, we use an alkyl halide. So when you take your amine and you react it with a methyl iodide, and it could be a bromide or a chloride, but iodide is the best leaving group, and so we usually use methyl iodide. We know, we talked about this reaction briefly in the last part. It's not a great way to make amines, primary, secondary, and tertiary amines, because it's hard to control. It will just keep adding. But we're going to use that to our advantage here. You're going to replace both hydrogens with methyl, and the lone pair will also pick up a methyl group. So you will get this ammonium-like ion, which actually is a great leaving group. But not only is it a great leaving group, it's a really bulky leaving group. So for the same reason that the bulky base gives the Hoffmann product, because sterically it's just easier to make, so does this Hoffmann elimination of amines. Instead of hydroxide directly, typically in this reaction, you're going to see silver oxide mixed with water, maybe a little bit of heat. It makes the hydroxide in situ, but is just commonly what you're going to see in this two-step reaction. It will leave in greater majority, right? So our major product, the less substituted double bond. And therefore, we call this the Hoffmann elimination. Now, you'll usually see this written in a 1-2, right? 1, your excess of methyl halide, and then step 2, your silver oxide and water. Now, just as a visual, the mechanism I'm not going to ask you for on the exam, but you know it. It's from chapter 7. Right? It's an E2 mechanism. It is concerted. Your base is picking up your proton, you're making your double bond, and you're losing your leaving group all at one bimolecular step. For an extra visual on why you get Hoffmann instead of Zaitsev, we can go to our Newman projections. Eliminations, or E2 eliminations, are anti-periplanar. So you're always plucking the hydrogen off that's anti to the leaving group. To get that hydrogen for the Zaitsev product on the more substituted side, it's going to put the larger part of the molecule gauche to that big leaving group. That is going to be higher in energy than this conformation, where we're looking at the hydrogen for that you would remove for the Hoffmann product. You see that larger part of the molecule does not have a gauche interaction with the leaving group. That means more molecules are going to adopt this lower energy conformation. So more molecules are going to be set up for the Hoffmann E2 elimination. The next part that we're going to get into is about diazonium salts, and it's a longer story, so I'm going to go ahead and cut this one short, and I will see you in part 4.